Log on, tune in, find out. Another good idea from Cambridge.
About singular integrals and bad neighborhoods. Number 1.
Thank you very much. So there will be 2 talks, and in both singular integrals will be in very bad neighborhoods, but in slightly different sense. So the interest of all that is, of course, the methods, the tools. But at least today, I won't be able to say too much about the tools, even though I will try. I will write down the names of the tools here, and maybe next time there will be much more tools than today. But today also I will try to say something. So the 2 tools which are kind of crucial to work with singular integrals when they are in bad neighborhoods, these are tools which are called so this is the first tool, and it's really a very discrete tool pertinent to the name of our program. The other one is another probabilistic tool. So some methods of stochastic optimal control come into picture. And this, I hope, will be quite prominent on the next lecture. So now let me try to describe what kind of problems I would like to talk about. So let's consider a couple of simple singular kernels. So that's one example. So here z and z are points on the complex plane, and it's a very simple kernel. And so if we put it like in a good neighborhood, meaning that both z and z are just points on the real line, so actually we are talking about such kernel, then it's known for like maybe 100 years that it's a wonderful operator which will be bounded in L2, or then it will be bounded in any LP, P between 1 and infinity. Maybe not 100 years, but for several dozens years. It's known what happens at the endpoints, so I don't want to mention that. So immediately let me show what kind of problems I have in mind. So let's now consider this kernel a slightly worse environment. So our thing on which we are considering such kernel is a Lipschitz graph. It also has a very natural measure. It's just length, which let me from now on start to use notation dh1. So h1 is a Hausdorff measure. And on the Lipschitz graph, if you restrict this Borel measure on the Lipschitz graph, it's just a sigma finite Borel excellent measure. And so again, you want to ask the same kind of question. Let's call the graph letter gamma. So same kind of question. And again, it's true, but it's now middle of 80s, and it took maybe approximately 15 or 20 years to solve it and to give the positive answer. It was known as a problem of Calderon. And Calderon himself proved this boundedness for Lipschitz graph with small Lipschitz constants. But then there are maybe a dozen proofs for arbitrary Lipschitz constant. but just to emphasize that as soon as you just change environment, made it worse, you come to real difficulties. So the next thing I want to mention, what if we just change this even more? So let us work on an arbitrary compact set. No, let's first, it's too fast to go to the arbitrary compact set. Let's just work on any curve. So gamma is just a curve on the plane, and we rectifiable. And we ask the same question. When Cauchy operator is bounded in L. So this is now 90s, and this has been done by Guy David. And the answer is very beautiful and very geometric. And the answer is, so if we denote this by mu, so the necessary and sufficient condition is that so necessary and sufficient condition that the length of any portion, so you fix a point on the curve, you fix a scale r, you look at the portion of this curve inside this ball, and this portion should have the length at most fixed constant times the size of this disk.
Is the necessity obvious? Is the necessity obvious?
Necessity of this, it should have been my next phrase, that necessity is obvious. I didn't expect it from the audience. It's not so obvious. It is obvious, right? Right. Necessity is sort of obvious. Okay, so now let's go to the arbitrary set. We have a compact set, and I want my measure mu to be a normal measure. Well, of course, it's not so necessary to be finite. Sigma finite would be enough, but it doesn't matter. So this answer doesn't work anymore. And the example is here. Okay, so what I did, I tried to build the counter set from the unit square. I took 4 squares of size 1/4 and then repeated this. Next time I have 16 squares of size 1/16, etc. Let's call this special E by special name, G 1/4, G in honor of John Garnett, who made very beautiful result using this set, and this set is exactly of this type. And of course, by self-similarity, you immediately see that this measure mu will of course have this property. Actually, it will be bounded from below and from above by constant times r. But there is absolutely no hope that Cauchy integral will be bounded here. And this is because the answer for the boundedness is very geometric, and here is the answer. So the theorem says that the boundedness takes place if and only if you take the portion of your set, and then there exists a Lipschitz image of a one-dimensional R, of one-dimensional Euclidean space. So Lipschitz image with fixed constants, so constants should not depend on x and r of this Lipschitzness of the image. And if you intersect this image with E and you compare these two numbers, they should be comparable. So in particular, if you have the boundedness on your set of the Cauchy integral, this set should have the property that there is a Lipschitz graph which intersects it on some positive measure. So G1/4 has the property that if you intersect it with any Lipschitz graph, of course the intersection, but this intersection is always 0. So such sets are called invisible or Bezikovich irregular. So Bezikovich irregular sets are interesting sets because Bezikovich, I guess working here, proved the following structural result. So structural result of Bezikovich. So if you have any E of the type we like, this E can be canonically decomposed into regular part, non-regular part, and dust. So non-regular part is exactly those guys. So there's a set, such set intersection with any Lipschitz. And by the way, you can change Lipschitz to rectifiable. You can change rectifiable to C1. All will be equivalent. So intersection is always has 0 length. And irregular is the part which actually is contained in the countably many C1 curves. And the dust, because we have some kind of canonical decomposition, dust must exist. Dust has just measure 0. So morally, what I just formulated says that boundedness is equivalent to this thing, to it being that, but more than this. It should be that quantitatively, right? So then it's the right answer. So this is a theorem which belongs to Saviatolsa.
So you mean quantitatively in the sense that there's a fixed constant relating
Yes,
these two?
yes. So each scale you just it's called uniformly rectifiable set. Such guys are called uniformly rectifiable. Okay, so before coming, you see, we are working with this very simple kernel, right? And it's two-dimensional. And what if we want to work in 3 dimensions, or whatever? So we have obvious analog of such kernel. Our kernel is complex valued, but you see it's exactly this thing in d equals 2 and s equals 1. Because if you take real part of Cauchy kernel, this will be exactly what I wrote. So,
to what extent is
excuse me?
the appearance of these rectifiable curves is somehow the result of the fact that you're using the H1 measure, right?
Yes.
I mean, is there something more general where you use?
So what I'm trying to say, you see, my singularity already becomes not 1, but S. Of course, I can do it even on the plane. Why should I consider only this case? I can, even on the plane, I still can consider any S. And there will be a singular kernel, and of course it becomes singular and interesting kernel if you consider that it, or them because it's a vector kernel, on set E with this property. Because, of course, singularity should match the size of the set. Otherwise, if the size of the set S is bigger than singularity, it becomes non-singular kernel and everything is trivial. If the size is smaller, it's trivial by the other way around because nothing can be bounded. Okay, so so before jumping to here, because it's again that's kind of one of the main topic of what I want to say, let us consider this example a little bit more because it's a very interesting example. So Bezikovich gave several conditions necessary and sufficient for the set with this property to be completely irregular, to be n set. And so that's one condition. Another condition, that almost every projection has 0 length. Okay? So in other words, if you drop the before needle on your set, the probability that it will intersect it under the condition that it intersects a bigger ball in which your set lies is 0. So this before needle probability is the same as projection of your set. So projection on. So you take a line on angle theta with respect to a fixed ray, you project, you take length, or h1, then you integrate, and this is by definition before needle probability. And for our set it will be 0. It's Bezikovich, because he gave necessary and sufficient condition and it's several equivalent conditions. But what if we try, in the spirit of our time, to be quantitative? And we come to the stage n, where we have 4 to the n squares of size 4 to the minus n. So it's just a very simple set. And by this result, we know that this is some epsilon n, which goes to 0. But how fast it goes to 0? It's unknown. It's unknown. So there are papers of Paris, Solomak, and there is a big paper of Terry Tao, which treats much more general sets, where he tries to give the quantitative version of Bezikovich result. And in these papers, the estimate, let me write it approximately because it's slightly different in these two papers, but not too different. So the estimate is something like what is logarithm star? Logarithm star is you count how many logarithms you need. You take log, 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 and the first time your number drops below 1, you count how many logarithms you need, and this is logarithm star. So it's extremely slowly decreasing function. Well, in the paper with Yuval Paris and Fedya Nazarov. So we actually proved something like that. And I'm mentioning that because it seems such a trivial problem, but it degenerates very fast to difficult things, reminding something about number theory. And so we have no idea what is. Of course, it doesn't look correct. And the best estimate from below we obtained with Michael Bateman, and this is that one. And of course, it's a good candidate for being the right estimate from above, but it's very far from.
Is 1 over n trivial?
1 over n is a simple result. If just 1 over n, it's sufficiently simple.
Is there a way to make this rate of epsilon n more intrinsic? Not something about not the specific choice of iteration or partitions, something more intrinsic of the set?
Well, let me tell you a little bit about that. That looks very strange. So if you do that, like a unit disk, and inside you choose 3 disks of radius 1/3, and you iterate, it will be exactly the same type of set, only 3 to the n guys of 3 to the minus n, again the same type of Bezikovich set, and epsilon n in this case is some small, so let's call it power estimate. So again, alpha is not very computable, but small, but yeah. It's sort of the same thing, but it doesn't use lots of symmetry, which one has in this situation. So then you can come to the next stage. You consider 4 guys of size 1 over 4, not necessarily like located like here. Again, iterate, and you get again the same answer. Okay, power estimate. Now you come to the 5 guys of size 1 over 5. And the method stops working. And there is a counterexample to the method. Not just we cannot do that, but there is a counterexample that shows that method doesn't do that. So we don't know power estimate in this situation. So this looks very stupid, but however.
But for example, in the Garnett set, is there some statement which would say, for every possible way to write it as an intersection of sets which are disintegrated in some way, the epsilon n goes to 0 in a certain rate? Quantitative. Instead of just being rigid and looking exactly this grid structure.
Probably.
So that would be something which is more intrinsic about the set and not a coincidence of who wrote you the sequence epsilon n.
Probably, yeah. I
So-
didn't try that, but probably. There is another funny thing, that if you consider this set, Garnett set, but random, could be many models of randomness. Here is one of these models. So you divide the unit square into 4, then each piece you also divide into 4. But here you choose randomly one of these, and here independently and randomly one of those. Then with large probability, epsilon n is equivalent to 1 over n. So it shows that really it's kind of very subtle. And so the answer in this random situation and the non-random situation are totally different. Let me tell you, so this looks like a very natural answer, but there is another very natural answer. Maybe even more natural, because as I said, that's related to the boundedness of Cauchy integral. Okay? So, of course, Cauchy integral is unbounded, but let's fix the stage and stop there. And normal, it has Lebesgue measure, but Lebesgue measure is too small. So you normalize to have unit Lebesgue measure on this collection, finite collection of squares. It has a very natural measure. And you consider a Cauchy integral operator on this thing, and you compute its norm. It seems like absolutely impossible task if we cannot just estimate geometrically how to project these squares, how we can hope to estimate the norm of the operator, which seems to be extremely difficult subject. But the Cauchy integral on this G1/4, as I said, normalized correctly, the norm can be computed. Unlike this in geometric things, the norm is approximately, again, two-side estimate is square root of n. So because this geometry is so much related to the norm, another natural answer, so this is one natural answer, there is another natural answer. And I have no idea which.
So in Tau's paper, if you quantify Bezikovich's theorem, you can relate the Favard length to the norm of the n theta rate in some way?
Yes, because there is a theorem, right? Which relates.
So what is the relation? Or
relation is not so simple. Okay, so we come to, so it's a good question, because here I can say everything I was talking about, I will put everything, I will put in the box and give it a name. So this is T1 theorems, okay? But there is another box, which is TB theorem. Oh, sorry, I have to jump to this TB, but I didn't finish unfinished thing. This RS, I should at least say something. It seems like, okay, we have this beautiful theory for S equals 1, D equals 2. Okay, just go and repeat. Technically difficult, maybe, just repeat. No way, it's completely open. It's completely open by a very strange reason. The reason is so-called Melnikov's formula. So let me call it hidden positivity. So Melnikov formula is the following thing. So if you consider the following function of 3 complex variables, which of course immediately reminds you that we are dealing with Cauchy integral, and we are computing squares, absolute value of squares of some Cauchy stuff. So if you take this function of 3 variables, and then sum up of a permutation of 3 variables. So Z permutes with W permutes with. Then up to some absolute constant, you get something, first of all, positive, and secondly, very geometric. It's just 1 over square of radius of the unique disk which comes through these 3 points. That's observation which I don't have words to not to praise, but to say that I just want to kiss his foot or whatever. I don't know. I mean, it's impossible, right? It's the most beautiful thing I saw in my life. Well, it's of course it's simple when you notice that, and it's extremely useful. So because you can come from this complex or changing sign kernel to positive kernel, lots of analysis becomes simple, and this is what works for this Tulsa theorem which I mentioned. If you try to do anything like that with any other kernel, you will succeed only once. With these kernels, and when S is less than 1. And the bad thing, or kind of insulting thing, that you will succeed trivially. If you put the S less than 1 and repeat that, you will see that it's positive by some obvious reason. But S equals 1 is the only difficult and correct case. S bigger than 1 is difficult but incorrect. It just false. There is no positivity.
You mean that thing's false?
Hmm? Well, any kind of expressions you try to make from RS's when S is bigger than 1, they are not positive. And so, again, sorry, postponing, but I,
Specifically for the Garnet set, it's probably, is it known when, for which S it's bounded? Specifically for the Garnet set.
for Garnet set specifically, specifically for the Garnet set, you now need to work with this thing when Z, W, and Z is on the Garnet set. And you just count how, you see it's self-similar. You just count how many triples of a certain size.
No, but this is S equals 1. For which S bounded on the Garnet set?
Yeah, well, you can consider, of course, Garnet set with other S. And try to do the same thing. And it will always happen that it's not bounded.
For all S.
Yeah, for these guys it's not bounded. But you will use very much this regular structure. Okay, so what I wanted to say. What I wanted to say, okay, it's kind of impossible. I mean, that seems like still a very kind of straightforward generalization of D equals 2S equals 1, so one should try to do something. And here comes a famous problem of Guy-David. So H D minus 1 is of E is finite and positive, and you have this all guys bounded. This is mu. So then E should be uniformly rectifiable. Meaning, meaning that, again, for each scale, there is a Lipschitz map of a small piece of Rd minus 1, such that it will intersect your set on sufficiently big Hd minus 1 measure. It's totally open. It's totally open even if you add regularity of E. So regularity of E is mu bxr intersection with E. So even if you add this regularity of the set, it's still open. So regularity doesn't help. So you may ask, why D minus 1? Well, of course, the general conjecture that you can put here any integer. And again, it should be true with or without regularity. By the way, a certain T1 theorem of Nazarov-Trail-Volberg says that with regularity or without regularity doesn't matter. You can reduce one to another. Okay, so this is again open except D equals to S, M equals 1, and M less than 1, but I stick to M as an integer. So what if M is not integer? So you don't have S-dimensional, you don't have 1.5 dimensional Euclidean space. So there is no way to have a Lipschitz map, a 1.5 dimensional space. So if this is, I don't know, where d equals 3, and this is 2.5, so what should be the conclusion? If it would be 2 or 3, the conclusion should be that there are Lipschitz pieces in your set, which intersected on big measure. So because there is no 2.5 Lipschitz pieces, so what should be the conclusion? Conclusion should be that we come to a contradiction. So in other words, if we have S, and our Ries transforms are bounded, we should come to a certain theorem of number theory, that if this is true, then S is integer. So that's not the simplest way to identify integers, but that should be the generalization of the conjecture of Guy David. So,
when you say should be, I mean, do you really have any evidence for this?
yeah, it should be. Everybody who worked in this stage believes that this is true. So this should be the first claim, and the second claim, because you already proved supposedly that S is integer, then E is S uniformly rectifiable. So this should be the full theory. It should look like that. And so it was open, and recently, maybe 2-3 weeks ago, so there is a small breakthrough. It's the theorem of Vladimir Eiderman, Fedya, Nazarov, myself, that so if S is between d minus 1 and d, we're done. Okay? So really, these non-integers cannot give us the boundedness ever. So one should understand it in this sense, that if operator is bounded, the set should be very symmetric. And sets of fractional dimensions, if they're symmetric, they're sort of countersets. And then they are not symmetric enough. So when d equals to 2, we have S here, and S here. So this is Tulsa. By the way, it's extremely difficult theorem. That's the one which I cited, the first one. So this is kind of, as I said, sort of much easier result, because positivity goes for free. And this is done by Laura Pratt. And this is the corollary of that. So at least in dimension 2, we know now everything. Okay, so yeah, so now let me jump to this TB theorems. So what is TB theorems? So they were invented by Guy David, Sams, and Sandrine Journet. And they say something like that, that if you have your Calderon-Zygmund operator and apply it to one function b and get something bounded, then your operator is a bounded operator. So of course, something should be corrected here, because if you apply to 0, of course you get something bounded. So you should avoid the zerousness, but that's the only thing you should avoid. So function b should be accretive. Accretive means that for every ball or every cube, the average, and there is an underlying measure because we are talking about L2 mu bounded operators. We want it to be L2 mu, so some mu should be there. And in our cases, this mu will HS on E or whatever. So if we have an accretive function such that its image is bounded, and you should say the same thing for the adjoint operator, but it doesn't matter, because in our case, all these guys are practically self-adjoint. Adjoint is just minus of the operator. So then there will be boundedness. So this CB theorem is a very powerful method to prove the boundedness of the operator, but it has two important features. So it should be accretive, and measure mu should have been homogeneous. So first, this David, Sams, and Journet theorem was just for Lebesgue measure in Rn, but then Michael Christ wrote a very beautiful paper where he showed that you can do the same things non-trivially. The only thing which is kind of enough is homogeneity of mu. Homogeneity means that it has doubling property. So you can work with operators on the metric space, and this metric space should be provided with such measure. And we know that metric spaces which can be provided with such measure are metric spaces where in every ball of radius 2r, there are like 130 no more balls of radius r which do not intersect. So geometric doubling. So in such metric spaces, there are such measures. You can consider Calderon-Zygmund operators. All theory works. However, there was a long link of results related to so-called Penlever problem. So Penlever problem was the following one. So you're given a compact set, and f is a bounded holomorphic function in C minus E. There is always bounded holomorphic function, 0, for example, or 1. We're interested in non-trivial, so non-constant. So the question was, describe E. So Penlever himself proved that our favorite H1E being 0 implies that there is no such functions, non-trivial. And in modern languages, it is written as analytic capacity of E is 0. So then, in 1919, Denjoy proved this. And in 1956, Vitushkin disproved this. Vitushkin gave a counterexample. Counterexample of Vitushkin was a very complicated counter set, and John Garnett, many years after Vitushkin, noticed that this 1/4 counter set gives the counterexample. So it's a counter set, and it doesn't intersect rectifiable curve. I mean, it does, but not on non-trivial measure. So there was
Was Donjua's mistake a sort of unfortunate technical one, or was there some conceptual problem that they didn't understand at the time?
excuse me?
The mistake of Donjua, was that a conceptual problem that they didn't understand at the time, or just a calculation error that?
Oh, you mean, yeah. I didn't read Donjua's paper, but what he did actually, the part of his proof was correct. So if you add to his proof that E was on the real line, then it's correct. And then people started to think, well, on the real line, meaning why on the real lines? Let it be rectifiable curve. So Vitushkin example was a counter set not on the rectifiable curve. It actually didn't intersect the rectifiable curve. Garnet, again, is of the same nature. So, but at that time, it was like 70s, people still didn't know many things. So they wanted to construct a counter set on the rectifiable curve, again, which gives like Vitushkin counter example. Maybe I told this story at the audience and somebody heard it, but it's a very beautiful story. Maybe I should repeat it. I was told that a certain colleague of Vitushkin, whose name is Dolzhenko, once met Vitushkin at the university. Vitushkin had a big pile of papers and said, you know, I constructed a better example. I constructed an example on the rectifiable curve. And Dolzhenko wanted to do that for many, many months or maybe years. And he said, give me these notes, I want to check, maybe simplify. And Vitushkin said, well, I can give it to you, but you should bring me a bottle of vodka for that. And Dolzhenko brought him a bottle of vodka, got in exchange these notes, and disappeared to check and work on them. And in a week they meet, and Dolzhenko was very sad. And Vitushkin asked him, well, what's going on? He said, well, it's very difficult. Yeah, I cannot understand your consideration. Your reasoning is very difficult. Vitushkin said, well, if you buy me another bottle of vodka, I will show where your mistake is. So now we know that that's impossible. There should be a mistake. So if your set lies on a rectifiable curve, then these things are equivalent. And even sort of more is known. So let me show you how it works. If you have a bounded analytic function outside of E, it can be represented by Cauchy transform of a distribution lying on E. So you have a distribution. I said this is bounded. If E has this extra property, then this distribution is a measure, absolutely continuous with respect to that. It's very easy to see. It's very easy to see. But this measure is a complex measure. It's kind of boundary values of this analytic function, which is bounded outside, sort of boundary values. Okay, so that's a complex measure. So suppose you have the following theory. So if compact set E carries complex measure such that this Cauchy transform is bounded and not zero, then there exists a positive measure, again with Cauchy transform bounded. Suppose you have that. So then, one can use Melnikov streak. One can write d mu zeta minus z. It's a bounded thing. Square. Integrate with mu. If you open the brackets, you will have exactly the expression which I mentioned. And if then you make the permutation, and they are permutation invariant, you will get a positive thing. So it means that this thing is bounded. This was bounded, integration is bounded. So your average curvature of measure is bounded. And this measure is kind of H1, or at least equivalent, absolutely continuous to H1. So there is some density. You choose a piece where density is bigger than small constant. So then you can replace this mu by H1. So there are lots and lots of triples such that 1 over r square, such that their curvature of this triple is small. So r is large, curvature is small. It means that there are lots and lots of triples which are almost like that, flat. And with big machinery, Guy David and Jean-Christophe Léger in fact prove that if this is finite, then a piece of your H1 must lie on a rectifiable curve. Okay? So in particular, if you start with bounded function, so in particular what I'm saying, that it just proves what Danjoy actually had in mind, that if E lies on the rectifiable curve, these things are equivalent. He had it in mind, but he didn't prove it. This is why it was called Danjoy conjecture. So this theorem actually is correct, and it's so it's Nazarov, Trail, Volberg. It's around 99, and actually a little bit more can be proved because it can be made quantitative. So if you normalize your boundedness and you want the measure with the same boundedness, and now you want to ask what is the estimate of this measure? How big is it? Zero measure always works, but we don't want zero measure. And the estimate is A Okay, and why it's important? So this is an absolute constant. Why it's important? Because if you work now with distribution, which is Penlever's original question, there is no way that you can assume that this distribution has a finite length of the support. You can, but it's just a particular case. So if it doesn't have this property, if H1 of E is infinite, and not even sigma finite, then you cannot use this theorem. But what you can do, you can surround this distribution by small disks and make the approximation. And approximation will give you the sequence of measures. They will approximate your distribution in the weak sense. Unfortunately, their total variation will go to infinity. And so if you look at this thing, of course you want just to come to the limit. You won't be able to come to the limit This will be kind of a fixed number. This will go to infinity. It doesn't go to infinity only in this case. And everything just collapses to saying that your limit measure is non-negative. Well, it can be 0, right? So there is no estimate. However, what Tulsa invented is that you shouldn't naively approximate this distribution by just very trivial, naive, say, mollifying of this distribution. Because if you do, you have measures nu n which will oscillate as crazy. And this oscillation is not needed to you. It gives some consolation which you don't want. So what Tulsa did, he invented cutting off the consolation. So he takes the naive measure, cut off the consolation correctly, and then he got a sequence of new measures where this ratio is not blowing up to 0. So even starting with distribution, it's true that we will find positive measure such that this thing is bounded. So whether you start with complex measure, whether you start with distribution, you always have a positive measure for which Cauchy transform is bounded. And then you can use the trick of Melnikov. So this positivity of measure was the key. And you got, as a corollary, for example, you answer the question of Vitushkin, that analytic capacity is semi-additive. And so this is how it works. So, and the key was this theorem, which is this TB theorem, where B is d nu, where this is B, a very natural B. The problem, there are only two problems. First of all, it's not accretive. It's absolutely not true that it's accretive. It's accretive only for one cube. And there is another problem. There is no theorem of Christ because measure, which is this measure, is absolutely arbitrary. There is no doubling, there is nothing. And so one needs to invent a TB theorem which is non-homogeneous and non-accretive. And it even should sound differently because you have accretivity only in one scale, so it just cannot be true that your operator is bounded. So what can be true is that you can find a piece on which operator is bounded. And how you find the piece, you throw away bad places. And it's always very tough because when you throw away water, you can throw away child with the water. So one should follow very carefully to show that the piece which still have a positive measure, and this is how this theorem is proved. And as I said, we're in an extremely bad neighborhood because there's absolutely no doubling, absolutely no accretivity, and still singular integrals survive in such circumstances. Thank you very much.
Are there any questions? No? Thanks.